All right. And thanks once again for another meeting. My name is Clement. For those who don't know me, my name is Clement. I'm a final year PhD student studying mathematics at Cardiff University in the UK. And then, so this is actually our fourth meeting. And this class is predominantly trying to do advanced data analysis in R. And the main focus is to promote mathematical programming among students from Africa, but anyone is also welcome to join. And the meetings are usually done on Zoom and recorded and also uploaded on YouTube. So everything we are doing is going to be on YouTube. And if you've not subscribed, please try and subscribe to the channel. And thank you very much for that support as well. So without wasting time, I will just share the screen for today's task. Um, so a minute. Okay. So basically, if you've not watched the previous video, so we've already had 3 meetings, and it was very insightful. So if not watched the previous meetings, I think it would be better to watch them before you watch this one. So this is actually the fourth meeting, and this is going to be the outline of my talk for today. Um, I think I might divide it also into two because I realized that most of the outlines cannot be done, everything cannot be done today. So we are going to divide it into two and then focus on the first half and do the next half next week before we actually start the actual statistical inference and also the models. So in our previous lessons, we learned a lot, and all what we've learned so far, it has got to do with trying to develop our own codes and functions to do a lot of descriptive statistics, and also looking at how to use existing packages to get customized plots and other things. Okay, so if you've not watched the previous videos, try and watch that. But so in statistics, we have two branches of statistics. Okay, so statistics can be categorized into the descriptive statistics and the inferential. So the descriptive statistics is where you are trying to summarize your data using these central tendencies and other summary measures and also plots. But the inferential statistics, but don't forget that with the descriptives, you cannot make any vivid or any conclusion with confidence. You can only say what the data is telling, that it appears maybe the percentage of females who prefer this particular maybe this particular drug is maybe higher than that of the females, but you cannot say that males are more likely to prefer the drug. Okay, so that's the difference between descriptive statistics and then the inferential. It is after you've done the inferential statistics that is the only instant that you can now make conclusions with some level of confidence. And in terms of inferential statistics, what we mean is that you're going to be doing a lot of hypothesis testing, and you're going to be doing other predictive models. So until we talk about models or start a hypothesis testing, you cannot make any vivid conclusion based on descriptive plots. Descriptive plot only gives insights. Okay, so it just gives us a fair idea of what is happening based on the data, but you cannot make any conclusion, meaningful conclusion from it until you have actually done an actual inferential statistics. Okay, so don't forget that. So now we are about to start the inferential side, but there were other things I felt we left that we need to cover. So we are going to now talk about a brief introduction to looping, and with loops we are going to talk about the for loop and the while loop. And then we're also going to make good use of apply functions. And with apply functions, specifically, we are going to learn about a function called apply function. And we're also going to learn about L apply, S apply, and T apply. You see what they all do, and it's very useful at a point in our analysis or modeling. And then we also learn how to store the results from the loops as a vector, as a list, and as a data frame. You understand what I mean by as a list, you understand what I mean as a data frame. For a vector, I think you already have a fair idea that I said is just a one-dimensional array. Okay, so see it as just a one-dimensional array. And where data frame becomes like a matrix. Every data can be seen like a form of matrix, okay, because it has some number of rows, it has some number of columns. But with a vector, it doesn't have it. Let's assume that it has only one row, and then in terms of columns could be the dimension. So if it is a vector with size 10, meaning that only 10 observations or elements or entries are in there, then you can treat it also as such. Okay, fine. And then the next thing is we are going to actually do a brief introduction to simulation. And by simulation, we are going to do something about simulating probability distributions. I will explain what is the use of these simulations and what's the use of probability distributions in the first place. And then we'll introduce a very powerful methodology called Monte Carlo Simulation. And this Monte Carlo simulation has a lot of tremendous importance. And when we get there, I would explain what it's also going to do. But we'll do that purposely for now for how to do a Monte Carlo simulation to simulate the toss of a die, and whether it's biased or it's a fair die. And I'll give an assignment where you would have to do it as for a toss or a throw of a coin. Okay. We're supposed to also prove a very important theory in statistics called central limit theorem. But for some reason, the central limit theorem and then the next one being some method of estimation, that specifically bootstrapping and jackknife estimation techniques, which I was supposed to also cover for this class, would be left out for this meeting and then done next week because it looks like we might not have time to cover all these for today. Yeah, we just want to be able to go at a better pace instead of just trying to speed up. And then don't forget that there will be assignment given maybe next week when we finish the other ones I wanted to cover. And then the R codes for today's class would also be uploaded on Piazza. So Piazza is technically a platform where we manage the class. So if you are not signed up to Piazza, you might not be able to get access to the script unless you probably contact me. And then if you want to enroll, you are happy to enroll, and it's free. Okay, we are just learning. All right, so now let's start something. All right, so the first thing we are going to do is called looping. Now with the loop, one thing we have to understand is that it's a way that helps us to actually obtain some outcomes that we would have done individually. We could actually do them together. Okay, but one thing I have to advise you is that if you have a very complicated model or a very complicated situation, some loops could be very slow. So always try and avoid loops when necessary, and only use them when it's necessary. Okay, so that's what I said here, that always avoid the loops, avoid loops if not needed, only use them when necessary. So when you want to do something like adding, subtracting, multiplying and dividing, let's say numbers or entries of vectors and so on, you wouldn't want to use loop for that because you can easily do that. You can easily do that without a loop. So that's what I started with this example. So what here we've done is that I explained to you that let me create a cell. I explained to you that if I type 1 with the column sign and 10, it actually gives a vector or a one-dimensional array from 1 to 10. Okay, and don't forget, when you see a function like sequence 1 to 10, when I run this one too, it's also the same thing. So I could have used, so there are so many ways. I could have just used the concatenate sign, the C, and manually type 1, 2, 3, which is a long process, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, but it's a long process. Meanwhile, you can actually use sequence to generate a sequence of numbers from 1 to 10. Suppose you want to generate a sequence of numbers from 1 to 1,000, you just indicate 1,000. But if you look at the regular increment, it's increasing by 1. Suppose you want it to increase, because here we have 1, 2, 3, 4, and so on. Suppose you want it to increase by 2, you can indicate by equals 2. If you do that, now it starts from 1 and goes to 3, 5, and so on. So you can actually use this to generate any sequence of your choice. And there are instances maybe you want to generate a sequence of numbers from 1 to 1,000, but you only want to produce only 50 of such observations. So you can write length dot out equals any number of any number you want, 50. So meaning that I'm generating a sequence from 1 to 1,000. However, I want to produce only 50 numbers from it. Then you just do this. So when you do this, is actually, so you realize that the first number, so you have exactly 50. Okay, but if you want to specify a particular increment, that is when you use the by 3 means it's going to increase by 3. and so on and so forth. Okay, so these are some of the things we'll be making use of. So don't. So when you see that, I think you'll be familiar with it now. So sequence, and then seeing something like, let's say 10 to 100 actually does is the same thing, creating sequence from 10 to 100, but with an increment of what? 1. But if you want to choose a specific increment, then you can use the function sequence and use by equals any regular increment you're interested in. Fine. All right, so now we've generated a sequence of numbers from 1 to 10, and we have stored it in something we call an object. So don't forget that what is the essence of object? So this X, I could have used any name for it. I could have used anything. The reason why we store results in an object is for us to be able to use it later. So you realize that now I'm adding X plus Y, because my X is actually sequence of numbers from 1 to 10. My Y is sequence of numbers from 21 to 30. Okay. So at this stage, I can now add. And then if I add, we have this. So meaning that to add two vectors is possible without any loop. Okay. So for instance, you can actually add, let's say I have some X1, and then I told you can either use the equal to or the less than with this sign. They both represent assigning. So now this X1 has been entered as an object, okay? So suppose I consider maybe a sequence of numbers, let's say from maybe 1 to, let's say 10, or let me say 1 to 20, okay? And then you can also use the semicolon if you want to write two codes on the same line. Or alternatively, you can just bring it down to the next line. So let's say 30 to 50, 30 to 50. I can add length dot out equals, let's say 10, meaning that I want to just generate or select 10 numbers from 30 to 50. So I would want to do the same thing for this one. Length.out equals 10. Okay, so at this stage now I've stored, so I could have just removed this one and press enter to bring this to the next line. See what happens if I don't do that. If I don't do that, I get an error. Okay, so meaning that you cannot write two different codes on the same line. The only way you can do that is to bring a column and it will work. Okay, or just come to the next line and type that. Okay, fine. So at this stage, you can easily add x1 plus x2, okay? And then you can easily subtract, okay? So when you do that, it does element-wise. Element-wise means that if we're adding two vectors, it adds the first element of the first vector to the first element of the second vector, then the second plus the second. So that's what I mean by element-wise. So meaning that something like this, you don't need a loop. But now let's see how you use a loop for this. But like I said, things that doesn't need, where loop is not necessary, especially when you're adding vectors, multiplying, subtracting, you don't really need a loop for that. It is when now it becomes a little bit complicated, then we'll see what I mean by that. Now we are going to make use of, first of all, the for loop. The while loop, we will learn about that later. So for the for loop, this is the basic syntax. If you remember, there was also a syntax when we are writing a function. I told you when you're writing a function, you start with maybe the function, you start with the function name, any name of the function, any name you want to give to the function, then you write function with some argument, you specify any argument you want, then you open your curly bracket and you specify any codes or whatever you want, and then you later return. So you specify, let's say, anything you want, anything, and then when you are done, you return your expected outcome. Okay, if you remember. So something like this is what we mean by the syntax. Okay, so for the for loop, what we are saying is that we always have to consider a variable. So this, I said val, you could use any letter for it, you could use any name for it, okay, in a sequence. So we always would generate a sequence, and within the sequence, we can open this curly bracket and write any statement we want to do, okay? So now we are going to use a for loop to do this same summation. So let's see how we are going to do it. So first of all, you always have to note that we can actually do this without storing the results, but let's assume you wanted to store the results. So we can actually just write. So for instance, here, I said for I, because I told you for the syntax, you always have to start with something in a sequence, okay? So, and don't forget, we know what X is. So let me open a cell up here. You already know that x is a sequence of numbers from 1 to 10, for instance. So here I'm saying that 1 to length of x. But what does length of x return? If you remember from our previous lesson, we said the length of a vector returns the size or the number of entries in the vector. Okay, so don't forget that. So the very moment I bring 1 with the column, it means that I'm equally generating a sequence of numbers from 1 to that. But instead of using 1 to the length of this, the smartest thing you can do is to use a function called sequence underscore along. Okay, so if you use this function sequence underscore along, you can actually use that to also generate. But in this case, don't forget that this 1 to 10 are not the actual 1 to 10 of x, but is representing the indexes of x. Okay, so meaning that x could have been anything. So suppose I change x to be, let's say, multiples of 5. Okay, so for instance, let's say sequence of numbers from 1 to, let me say from 5 to 1,000, and I'm increasing by 5. Okay, so in this case, now you realize that my x, let me specify x here. You realize that my x are multiples of 5 now. Okay, so but if I consider sequence along s, I have 1 up to whatever. Okay, so now the sequence is just extracting the index or the positions. So for instance, if I consider, let's say, the first 5 numbers, let's say the first five numbers of that sequence. Okay, so that is x. If I consider the first 5, I have just 5, 10, 15, 20, 25. But the very moment I consider sequence along, see what happens. So it meant that this one is just returning the positions. And that is exactly what you need in any for loop. So for for loop, you mostly see I or K, anything in that sequence, okay? And what I'm saying is that instead of using the y is to the length, which usually people do, you can actually use this sequence. When you use the sequence, whatever is there shouldn't necessarily be numbers. S could have been a name, let's say males, male, female, and you realize that anytime I'm writing a string or something which is a number, I bring a quotation and specify that, let's say mixed. Okay, so for instance, now if I should run x, you realize that x is just something which is a factor or something which is not a number, right? So in this case, the very moment I type sequence along s, let's see what happens. It just returns the positions, and that's exactly what you need. So technically, I can just replace this one by sequence along x. Okay, so don't forget that. And don't forget that you can only add 2 vectors when they have the same length. You cannot add a vector with, let's say, with 10 entries and add it to a vector with 15 entries. It doesn't work that way. The same thing with matrix addition and multiplication. You cannot multiply or add matrices if one has a different if one has a different dimension. Okay, we would actually talk about matrix 10 algebra, but it's not for today. All right, so let's continue. So one thing I want you to keep in mind is that now our x is a sequence of numbers from 1 to 10. So let me just run what we have up here. Okay. All right. So here we are saying that for I in sequence along S. So the sequence along S is returning all the positions of the element in X. Okay. You could have just used 1 to the length of X as well for the same thing. Now we want to save the output of each of the summation. Okay, now we are going to add x and y, and you realize that here we just needed to just say x plus y, and it does it for us. But now we are trying to use loop to achieve this. So now, and if you remember, if I should run x here, we said we can use the square bracket to extract. So if I want to extract the number at the 5th position, I just have to put 5 here, and it will extract the number at the 5th position. Okay. All right. So don't forget that this 5 here is position, but the number at the 5th position was 5. Okay. So don't forget that. So now, here I'm extracting each position. So now look at what is happening. It's saying that for I in each of the position from 1 to let's say 10, okay, because the sequence is from 1 to 10. Now what it's doing is that extract the first element. So when I is 1, so you start with, because I told you the sequence of x actually is numbers, positions. So don't forget, these are the actual positions from 1 to 10 of each of the entries. So it will first of all pick the first one and say that if I is the first one, first of all, extract the first position of x plus the second position of x. And we want to save the results into an object called results. But you realize that the object, if I ignore, if I bullet, as in if I put hashtag in front of the first one and I run this one, I'll get an error because it says this object is not found. Okay. Now we want to be able to also save the results. So, and saving the results is very important. We'll later see that we will even be using for loops to be plotting and to be doing a lot of things. So what you need to do is that if it's a vector you are trying to save, you can use numeric of any number. So now if I type numeric in bracket, I put 5, see what happens. I've considered a sequence of numbers, I've considered a vector with entries being 0. Okay, so always keep in mind to save a vector, okay, or to save each element of a loop. You always have to create a space for the actual results to be saved inside. It's more like you are trying to put a book in some shelves. If the shelf or the shelves are, let's say, full, or there's no space, you cannot put your book in there, right? So that's exactly the ideology. So it's more like you always have to create like a holder where you can now put the results in there. So you can either use anything. So sequence of zeros, you can even use sequence of, let's say, NAs. Let's say if I want to, so if I run repeat and repeat, so REP means repeat NA 5 times, okay? So this one is repeating NA 5 times. You can use false, true, whatever you want. So all you need to do is that just create an empty vector, but the empty vector could be made of zeros, or it could be made of NAs, could be made of false. So here you could see that I said that it's either numeric, or you can use replicate. N is how many times the length of x. The length of x was what? Was 10. Okay, so meaning that it's replicating any 10 times, or it can replicate false. So when you do that, now if you run this one, it means that I can now, so it has first of all considered extract when I is 1, consider the first entry plus the first entry of y, then put the results in the first entry of the results folder. So meaning that, see this one like a folder, where now the folder being a folder. So if I should run this one, I now have a sequence of I now have a sequence of zeros. How many times? 10 times. So what is doing is that after doing the first summation, the results will go and replace this 0. Then after doing, when I is 2, it extracts the second observation or number in X, and also the second observation in Y, and replace this second 0 with the results. And that's basically what this is doing. So this is one of the ways you can always save your results, your results if you are using loops. And you can compare this results with when I just did X plus Y. If I do X plus Y, if I do X plus Y, I get the same answer. So you realize that in such an instance, using a loop is just a waste of time, because technically just X plus Y will give me the results, okay? Now let's go on. And then, so here, I was just trying to tell you that you can replace, instead of the numeric, you can also replace it with replicate NAs, or you can use anything. So right now, suppose I also use this and run. Now the same, I've not changed anything. But when I was saving the results, previously I was using a vector of zeros. Now I'm using a vector of NAs. I can replace this one. If I say vector of NAs, if I should type this, you realize that initially they were all NAs. So when it extracts, when I is 1, it extracts the first entry of X, plus the first entry of Y, then it replaces, it saves in this results folder, but replaces the first entry. So that's why here I brought a single square bracket. So don't forget, here we use a single square bracket to extract vectors. So here I'm extracting the first position. So it's this 22 actually replace this NA here. And then the next one will come. So when I is 2, then it's also the results is saved in a second, and so on. Okay, so these are just the same thing, literally trying to explain that you can either create sequence of zeros to save your results, or you can create sequence of numbers or letters. Will you believe that I could type anything here. I can type my name and still run and still get the results. Okay, so here I just use my name, anything. So here, so that's what I want you to keep in mind, that you can literally create sequence of zeros, sequence of variables, or sequence of letters, whatever, and it will still work. Okay, so here we are just trying to use something familiar, so that's why we used any. Okay, I could have just used true. I could have just used true, and I have my results. I could have just used false, anything I want, and I have my results. Okay, so this is just how you will be saving each results in the loop. So don't forget that for the loop, it's first of all consider the I here is just representing the positions you've specified here. So it's to start with the first position, do everything it will do with the first position, then it will go back and continue with the second position and come back and do everything and save the results here, and it will go to the next position and come and extract, do the summation and save into the next position in the results object. Okay, so that is how easy. So now I did the same thing here. I only changed the results holder to using numeric for with sequence of that zeros, and here I use false. I just wanted to see whether the results 1 and 2 are the same, which we can clearly see they are the same. But you can use this function all dot equal and specify whatever you want to compare. So what the all dot equal does is that it tries to compare whether all the entries of the results and then results 1 and results 2 are the same. So if you run and it says true, then it means that every single entry in results 1 is actually equal to every single entry in results 2. So you can actually use this one to compare if two different data frames or two data frames are the same. You can use it to compare if two matrices are the same. You can also use it to compare if two vectors are the same. Okay, so don't forget that. Now, there are other things we need to know. We learned previously that to divide, let's say, we can use R as a calculator, if you remember. So I said, if you consider, if I write 2 divided by 4, this is what I would just write. Okay, if I want to multiply this 20 divided by 4, this is how I would just write. Okay, so this slanting to the right is division. If it's multiplication, I use the star. Okay, and it also does multiplication for me. If it's addition, the normal addition, it does. If it is subtraction, it does. And then suppose I want to add 20 and 4. You know, I can also use a function called sum. And then instead of writing 20 plus 4, I will just create a vector, which is, let's say, 4 and 20. If I do this, it will give me the same answer. Okay, so keep in mind, at a point, we'll be using sum. It's not always that you can be using the normal plus sign. There are instances you get, so for instance, the results folder that we had, okay, the results 1. Now, suppose I want to know the sum of all these. You know, clearly I cannot use sum here. The only way I can use sum, if I cannot use addition, sorry, I cannot use the plus. The only way is to rather create a loop around it, or just write sum around this, and it will sum all the entries in here. Okay, so that's how simple you can sum all entries in a vector. Okay, or you could even sum all entries in a matrix just using the sum function. All right. Now, so we've learned that 20 divided by 4, it works. But the very moment you use 20 with a percentage sign and 4, just 1%, you get an error because it doesn't exist. Okay, with just 1%, you get an error. But if I use a 2% sign, look at what happens. It returns 0. So this 0 is returning is what we mean by the modulus. So if you remember in mathematics, when you say that find the modulus of two numbers, let's say the modulus after you divide 20 by 4, it means that if I divide 20 by 4, what is the remainder? Okay, so suppose I consider divided by 3. You know, technically 20 divided by 3, and you are going to actually get 6 remainder, what? 2. So if I run this one, you realize that the 20 with the double percentage sign returns 2, meaning that this double percentage sign returns, so I explain it here that the double percentage sign returns the modulus or the remainder after dividing what? The 20 by 3. Now, the very moment you bring the division sign, so now let's look at the difference between these two. So suppose here I make here, let's say 3. Let me consider 3. So 20 divided by 3. Now see the difference. 20 divided by 3, this is actually the full answer, okay? But when I bring percentage sign before the division and after the division sign, it only returns the whole number after you divide. So you realize that the double percentage sign retains the remainder, whilst the double percentage sign with a division sign in between returns the whole number. Okay, so it means that if I divide 20 by 3, you realize that we have 6 point this. It returns just the whole number part without any other. Don't forget that this part will go into the remainder, or this part will just reflect the remainder, but it only returns the whole number. If so, meaning that I can divide, let's say, 1,000 by 3, and I'm just interested in the whole number part. I can use the double percentage with a division in between, and it will return just the whole number. If you want to know the actual value, when you do the actual division, this is what we get. So don't forget, when you see these things, because you are going to make use of them, okay? We'll explain now. All right, so now with this, now we are going to introduce a particular concept, because we are going to create some sequence. So for instance, you can be asked to find how many maybe even numbers. So if you remember, those of us who started with mathematics, don't assume that these things are not going to be relevant for your data analysis. It's really going to be relevant. So that's why we are starting with these basics, and then we will see the use later. All right, so if you remember, you could be asked to find how many even numbers are there from, let's say, 1 to about 54,859. How many even numbers are there? How many multiples of 5? How many multiples of 6? Technically, there's a way you can actually calculate that mathematically. But if you're using a programming software, you don't have to think at all. You just, if you know your coding, you just get your answer straight away, okay? But keep in mind, if I'm talking about multiples of 2, what does it mean? You see, if I create a sequence of numbers from 2 to, let's say, 1,000, okay? And I say by equals 2. This is a way of creating a sequence of even numbers. Here I said it should start from 2 to 1,000, but the regular increment should be 2. If it's a set of odd numbers, you know, odd numbers also has a regular increment of 2. But it starts from 1, okay? And if I do this, it will actually create a sequence of odd numbers for me. But what about situations where you have a particular sequence and you want to extract only the even number part? Okay, so that's basically what I'm trying to ask you here. So now, suppose I'm creating even numbers now. So suppose so this is the sequence of even numbers. Now let's look at this critically. If something is a multiple, if something is an even number, it means that that number divided by 2, okay, is supposed to give us a remainder of what? It's supposed to give us a remainder of 0, if you think about it critically. So anytime, so because 4 divided by 2 will just give a perfect whole number, right? And the remainder is 0. So it means that if any number is actually a multiple of 2, or 2 can go into it, it means if I bring the double percentage sign, okay, this double percentage sign returns the modulus, or the remainder, don't forget. Okay, so it means that if a number is divisible by 2, and I just bring that number, so if I want to know whether 88 is divisible by 2, and I bring the double percentage sign, and I get the remainder to be 0, then it means indeed that number is a multiple of 2, okay? If I want to know something is a multiple of 3, so for instance, this one, I want to know whether it's a multiple of 3. Is 88 a multiple of 3? If I run and I get something which is not 0, then it's not. Okay, so these are some of the things you have to keep in mind. So now the first thing is we have a sequence of numbers from 1 to what? This huge number. I want to only extract multiples of 2. Okay, so I've explained about 3 different approaches of how you go about this. So the first thing is that we've created that sequence of numbers from 1 to 54,859. And now at this stage, I was only counting how many even numbers. But the next one, I would want you to extract and tell me all those even numbers, and also tell me the actual number of even numbers, okay? So at the moment, I'm trying to look at how many even numbers. So see what I did. So here I said for val in, don't forget that I could have used I could have used K, I could have just used K and then change the val to K, and I'll still get my results. Now, this is what I'm doing. Here, I'm not interested in saving the output. I'm not interested in saving the output of the loop. So you realize that all I did was I didn't bring anything like numeric anything like replicate or whatever to save the output of the loop. For here, I'm just interested in calculating how many even numbers are there. So look at what I did. So I first of all set something we call count equals 0. Don't forget the less than minus is the same thing as equal to, so it shouldn't be a problem. But the actual equal to is what we mean by double equal to. So the single equal to is just for assigning. It's just like the less than with this, okay? So now look at what I'm doing here. Now we already know that n is from 1 to what? A certain number. So if I just specify n without writing, I could have, if I write 1 to n, I'll get something different. You could have just used 1 to n and you put length around this, okay? Or you can just use sequence along. The sequence along, I think, is the best thing. If you do that, you don't have to worry about specifying 1 to something. So right now, I've just used sequence along n. So it's just going to extract each of the positions of the numbers in n, okay? So what this one is doing is that, first of all, it's considering every, so don't forget, if I should specify, let me open a cell here. If I specify n to be let's say 10, n to be let's say 10, okay, or 1 or 11, the sequence along 1 to 11, or let me say 11 to 20. The sequence along this is just telling me that we have, these are the positions, okay? So if you use the sequence along, don't confuse the sequence along with the actual entries. So the sequence along is just returning the positions. I think I've already explained that. So what this is doing is that it's considering the first position in the sequence 1, okay? So now I'm considering n from, the n range is actually a vector from 1 to 54,859. So it considers the first position and ask from here, there's an if condition. If you've watched the previous meetings, you realize that, or the previous YouTube videos, we started with conditions. So here I'm saying that if if the position, okay, so don't forget that this k is representing the position, because I said for k in the sequence along, and the sequence along returns the position. So the first value of this position is 1. So it's first of all asked, is 1 is the modulus of 1. So if I divide 1 and 2, with the modulus, don't forget the double percentage is modulus, or it returns. So meaning that any number with a double percentage with 2 would return the remainder after I divide that number by 2. And we are saying that if that remainder is actually equal to 0, okay, then it means that clearly it's an even number, isn't it? So then it means that now the count, I started with 0. So here, if and don't forget, anything you specify outside a loop or outside a function, inside the loop, it will recognize that the first count value is 0. So here it will consider 0 plus 1 and store it. So 0 plus 1 is what? 1. And it will give this count to be 1. So meaning that it has counted the first even number, if indeed it's an even number. Then it goes, so for instance, for 1, when k is the first position, we know that the first position 1, the number in the first position is actually 1, okay? And 1 divided by 2 will not give us something whose remainder is 0. So in that case, this count will still so in that case, it won't even come here for us to consider that number as an even number. So once it's an even number, then it will start. So suppose I put 2 here, then it means that if that condition holds, then the count here was initially 0, so it will be 0 plus 1, meaning that we now have one even number. If k is 4, then if that condition holds, then, so don't forget that for the if, it's only when the condition holds, then it runs everything there. I could have brought a curly bracket around this and close it like that. If you remember, usually when I write the if condition, I can either write the if condition, bring a curly bracket, and write whatever I want to compute if that condition is satisfied. But keep in mind that if it's just a single line, you can choose to ignore the condition. Okay, you can choose to ignore the curly bracket. Okay, so here I can choose to bring the curly bracket down and still run. I'll get the results, or I can just bring the curly bracket on the same line without even the column sign, and it will still run. Okay, so keep in mind, or just to make life easier, you can just bring a curly bracket around that, so that we know if this condition holds, then it should count. So that's basically what is happening here. Okay, now if you come to the next approach, now what I'm doing is that here I wasn't saving the even numbers. I was only counting how many even numbers. So if that condition holds, that number is an even number, then it should increase the count by 1. So if the number is not an even number, then it doesn't even come inside here. If it's an even number, then the count will increase by 1. So it will continue for all values of k till the last number. Then you realize that it meant it started with the counting. So if you want to see what is actually happening, let me just reduce this to, let's say, 10. Okay, and then let me try and print out count and see what happens. So let me close it. Let me comment that. So now see what happens. So so here I've considered numbers from oh, sorry, did I say print 0? Print k. Okay, so here see what happened. So what happened was it first of all considered when k is 1, and since it wasn't even number, it didn't even come inside this condition. Since when k is 1, when k is 3, it doesn't even, because it doesn't satisfy this condition. So it's only those values of k that will satisfy this condition that will get counted. Okay, so here you realize that the positions that satisfied, or the numbers that satisfied the position or the condition, were actually just 2, 4, 6, and that. Okay, suppose I divide here by 3, then here I'm trying to extract the multiples of 3. Okay, or let's say odd numbers. Okay, so here if I should run this one, you realize that it is only 3, 6, 4 that what satisfy the condition. So suppose so if it's only this 3, then I expect the total number of odd numbers to be 3, right? Because it's only 3 numbers that satisfy the condition. So you realize that if I should ignore the print and just consider the total number of odd numbers, I get what? I get 3. Okay, so don't forget about that. So now it was for even numbers, and you can always print out to know which ones satisfy. At this stage, I'm not only interested in just printing out the results, or printing out how many even numbers are there. So with this function, you can use this one to create how many let's say multiples of 5. Suppose I want to know how many multiples of 5 are there from 1 to this. All I need to do is to specify 5 here, because we know that if something is a multiple of 5, when we divide by 5, okay, the remainder should be what? 0. So once I do this, I just change the 2 to 5, and I run, it will give me that there are this total number of multiples of 5. If I'm interested in multiples of 7, just put 7 here. It will tell me how many multiples of 7 are there from 1 to that. Okay, so that's how interesting the for loop can actually do for us. So now it's just even numbers. All right, so now at this stage, suppose I'm now interested in knowing the even numbers itself. So here I explained 2 ways. Okay, so initially I told you that for results in a loop, you can save them as a vector, you can save them as a list, and you can save them as a data frame. If I say as a list, what do I mean? So now, instead of writing numeric, if you remember previously, we were writing numeric, and then we put the length of the length of whatever we want to actually consider. Okay, but look at situations where now we don't even know how we want to know the actual numbers. Okay, the actual multiples of 2. Okay, from 1 to that. Okay, now we don't even know how many of them will be multiples of 2. So if we are to create a sequence, let's say a sequence with let's say 1,000 a vector with 1,000 entries to save the results, you are only trying to tell them that only 1,000 numbers will be multiples of 2. Meanwhile, it could be more. So since we don't know the exact number of or the exact multiples of 2 from 1 to this, suppose we didn't know, we could have known from here. Then all I need to do is to use a list. Just say list with an empty bracket, or you could have used a C with an empty bracket, or you could have just used NULL. Okay, so whatever I run here, when I'm done, you can just change it with, instead of the list, you can just use a concatenate with an empty and see what happens. Okay, so fine. So here I'm creating a list. So you see what I mean by the list. And if you remember when I was saving the results, now what I'm saying is that instead of n, so here is because the n is already from 1 to that, okay? So the n is already from 1 to a certain number. Or I could have just used sequence underscore along in bracket of n, and it will also do the same, fine. So here what this means is that for any number in n, for the first one, it should test whether it's an even number, okay? Whether it's an even number is given by this. And if it's an even number, that particular number should be saved in the list. But remember previously when it was a vector, I was using I would have used a single square bracket. But don't forget that when it's a list, we use a double square bracket. So this one is, if it was a vector, if I had created the multiple underscore 2, if I had written numeric of something, or if I had written replicate of something, then I would have used a single square bracket to extract or to save each entry, right? Or each result. But if it's a list, you use double square brackets. So that's one thing you have to keep in mind, okay? And now let's see what happens. So if I run this one, wow. It said value. Okay, sorry, it's val. So I told you whatever you put here, it can be k, it can be I, it can be anything you want. Okay. So now when you run, first let me just remove this, and now let's see something here. So let me comment this one. So now if I do this, so if I run and I put 1 here, it will extract the first value. So this is how, after running, because this is going to be a very long thing, okay? So that's why I didn't print everything out. Okay, if it was a vector, if you remember, we use a single square bracket to extract the first entry. Now, if I use a single square bracket, it also works for some reason, but there are instances the single square bracket might not work when you're extracting. So when it's a list, you use a double. So when I put, let's say 2 here, it's going to extract the second number or the second number in the list. Okay, so this is when it's a list, we use double square bracket to extract each entry. Keep in mind, that's the difference between when you have saved the results as a vector and as a list. All right, and then now if I should run everything, see what happens. So now these are all the multiples of 2. Okay, so these are all the multiples of 2. So so what I did here, I used the unless function, and the unless function is if the multiple of 2 was actually a list as we saw, I could use unless to convert it to a vector. So now if I should just run this one, I use unless of this one. To unless means that now convert the results or the output to a vector. Okay, so that's what I did. And now typing the length of that will give you the total number of, so this will give you the total number of multiples of 2. And then if you now want to know the actual multiples of 2, you can actually run this and see all the multiples of 2. Okay, so basically that's what this session did. All right, so now here what I said was, how many multiples of 8 are there from 1 to 1,000? So suppose that was another question you were given, and you were asked to use a for loop. How many multiples of 8 are there? So we realize that it's the same thing we're doing here. All you need to do is to change, instead of 2, put 8 here, and then the modulo should be 0, right? Because I said that's basically what we are doing. Okay, so what I'm doing, we've already done a similar thing. So I could have just used a vector, but I told you, because if I use a vector, now let's try and use a vector instead of a list. So suppose I want to save this one. But I chose to use, let's say, replicate NA, and then I'm doing it how many times? Length of N, okay? So in that case, I have to use only, if I use double brackets here, double square bracket, I'll definitely get an, let me close, let me bullet this one. So when it's saved as a vector, use a single square bracket. Okay. So when I use a single square bracket, now let's see what happens. So you realize that now what it's doing here is that, oh, okay, is because I initially, let me bullet this one first. So now if I should use a square bracket, let's see what happens. So at the moment, I'm creating a sequence of n's, okay? So I told you the replicate n how many times? The length of n, okay? and then I'm going to save all those multiples of 8 into the vector. Okay, so it meant that it when the first value of k satisfies the condition that is a multiple of 8, then that one should be saved in the first position of the object multiple underscore 8. Now I've used a double square bracket. Meanwhile, I'm creating a vector to save. See what happens. So at the moment, um, when I do that, with this one is working for some reason, but technically if it's a vector, just use one bracket to extract. Okay, all right, so now let's see. Because originally I didn't know how many multiples of 8, if I should now create a sequence of numbers, so now here we have 1,000 numbers. Okay, and I want to know how many multiples of 8 are there, and I've created a sequence of n is 1,000 times. And here what it's doing is that it said the first number was not a multiple of 8, the second was not, the third was not, the fourth was not, the fifth was not, the sixth was not, the seventh was not. It was the eighth number, which was actually, or the eighth position, or the eighth number, which was actually a multiple of 8. Okay, so you realize that if a particular number is not a multiple of 8, it returns any. But this one can be a little bit stressful. Just imagine if you want to now tease out, suppose it's a very long sequence. Okay, so what I did was, so that's why it's not advisable if you don't know the actual sequence, okay, or you don't know the actual multiples of 8 you are expecting. You can just create it as a list. You can just store it as a list and use double bracket here, okay. And then when you do that and you run, now see something here. You realize that since I save it as a list, I am now getting the first position is empty, the second is empty. It's only the if that something is there. And I told you can now use a square bracket to extract. So now if I extract the first one here, for instance, and I run, it gives me now because the first number was empty. Okay, so that is why I use something called onList. So what the onList here, so what the onList does is that it converts it as a vector. And onList sometimes automatically removes any missingness. So the now part, it removes it. If the empty part was there, you could have just put something called na.omit. You see that shortly. So meaning that this is how easy we can actually extract the actual multiples of 8. If it was multiple of 9, just put 9 here, okay? And then we expect the modulus to be 0, and then you save it as a list, and this is how we save. So if that number holds, if the condition holds, then that number should be put in their respective positions and so on. So that's basically what we're doing. Now, if I want to return or to know the total numbers, I just use something called, I could have just run length of multiples of 8 to give me the length. But sometimes you can also, if you want to, here I'm just trying to write the total number of multiples of 8 is that. So I could just write, I could have removed the print and then take one bracket here, and I'll still get what I'm looking for. Okay, but sometimes you realize that if I put a print, it only brings something in front, which is not really necessary. Fine. All right. So you can actually go through this. So I wouldn't bore us with this and go on to the most important thing. So this one was another approach, doing the same task, but it was another approach. And this time around, instead of using list in brackets, I only change it to now, and it also does the same thing. Okay. But now let's look at something. When I use the list in brackets, and then I try to run it without onlisting. Okay, so here I use onList function. I could have chose not to use onList, and then it was still the multiples of 8. Look at what happened. It's run and it's giving me the now, where when it's not satisfied, it just return now. Okay, so what happens is the onList around it would only what convert it to a vector. As we saw, it will convert all of them to a vector and remove all the nulls, as we saw, okay, by just onlisting. All right. So here, what I did was I changed the list in bracket the list with the empty bracket. This one, I changed it with now, okay, because I told you that you can actually use this, or you can use now, okay, and you can even use a concatenate sign without anything inside. and they will still work, but sometimes they have their discrepancies. But I would want you to go for this one instead. Okay, it's better and it saves time. But now I use now. Now let's see what happens if I use now and then I run. Now you realize that it returns NAs, and only instances where it is satisfied, then it brings it tells me the exact number. Okay, so that's one of the difference with this one. It was telling me now, and it will just give me when the number is satisfied. So the very moment I use on list, it only extracts those multiples of 8 for me. But at the moment, if I use now here, so what the null is doing is that it's just the same thing as saying replicate NAs. Okay, so it's just doing the same thing as the replicate NAs, if you remember. And then when the condition holds, then it just gives me the exact multiple of 8, and then meaning that then 9 was not a multiple, so NA and so on, so 16, that kind of thing. All right. But now, if I should use now and I should run, this is what I'm getting. The only way I can remove all the NAs is to use something called na.omit. Now let's see what happens if I use na.omit. So what the na.omit is doing is that it is going to remove all the NAs and just return just the numbers, as you can see. So so suppose you have even a data frame and it has NAs. You can actually use na.omit to remove any NA in the data frame. In that case, it will remove any row which has an NA in any of the columns. So meaning that suppose on row 10, there's an NA for a certain variable, it will remove the entire row from it. Okay. So the na.omit is actually another way of removing NAs from a vector, from a data frame, or even a matrix. So don't forget that. Okay. So yeah, so doing the NA of that will the na.omit will remove all the NAs, and I'll still get the same results as I was doing previously. All right, so let me just bullet that. Okay, so basically now it's telling me, because I was interested in the total number of multiples of 8 as well, just putting length around the multiples of 8 will also tell you how many observations actually satisfied, right? So it also tells you that there are actually 125 numbers that are multiples of 8 from 1 to 1,000. Okay, now that was the for loop. Everything will uncover very soon. Suppose I wanted to achieve that with a while loop. So all what we're doing, so here, suppose I want to know how many multiples of 8 are there from 1 to 1,000 without what? Without using a for loop but a while loop. At the end of the class, I'll try and just give a brief summary of everything, and you understand everything. And don't forget to watch the video at your own pace, and then with that too, you'll be able to appreciate. But very soon we'll see the main use of the for loops, and this is just an introduction, and then we'll see all the use. Okay, so fine. So suppose I wanted to use a while loop. The syntax for while loop is a little bit, it's similar to the for loop, but it's a little bit different. So you realize that for the for loop, the syntax was such that when I come up here for the for loop, yeah, the syntax was, it considered for something in a sequence. Okay, but for the while loop, what is going to be here is going to be a condition. So now let's come down to the while loop. So here, what I'm doing is I'm using, let me come down. Yeah, I'm using the while loop. So here we are saying that for the while loop, the syntax is said that inside here is going to be a condition, any condition of interest. And then you open your curly bracket and then you put any statement you want to satisfy. Okay. And don't forget that we use the if and else if you want to specify a condition. So don't forget, I only say if something holds, then it should do something. So anytime I say if something holds, then I can bring a curly bracket. If it's just a single thing, I can choose not to bring a curly bracket. Here I could have just brought a curly bracket around this one, okay? Or I could have just pressed this for it to come down like this, as we've already been seeing. But if it's just a single thing, you can choose to ignore the curly bracket. Fine. So here you realize that for the while, what it's saying is that we are considering multiples of 8 from 1 to 1,000. Okay. So here you realize that I didn't have to generate a sequence of multiples of 8 first. But when I was doing for the for loop, I had to I didn't have to create a sequence of numbers from 1 to 1,000. But when I was doing for the for loop, I had to generate a sequence of numbers from 1 to 1,000. Okay. So if I'm doing the for loop, you just have to start with the first number. Here, the first number was 1. 1 to 1,000. Here, all I need to do is the first number, and the last number is put as a condition. So here you realize that as in the case of the for loop, I start with for, let's say I or k or anything in the sequence from 1 to the total number of observations in the vector. Okay. Now, when I is 1, it should do something, save the results, and go to when I is 2, do something and save the results. So that is basically what the for loop was doing. Okay. But for the while loop, see what happened. I had to start with the first number. Even though I'm generating, I want to first of all consider numbers from 1 to 1,000, but I'm interested in multiples of 8. And here I'm saying that if the n is less or equal to 1,000, it should stop. So that's what the while loop does. So for the while loop, if you don't put a stopping condition here, it creates something we call indefinite loop. Indefinite loop means that the loop will not stop. If you are doing it in your R studio, you realize the code will be running and the output will never be coming because you didn't tell it to stop when a certain condition is satisfied. So keep in mind that for the while loop, you always have to put a condition such that once the condition holds, then everything should stop. Or once it does everything and it gets to that condition, it should stop. So here we are saying that n is 1 equal to 1, but when n is at most 1,000, it should stop. So that's what I'm saying. And now you put the condition here instead, okay? And look at the for loop. I just had to consider for something in this. Then I consider the condition, and if the condition holds, that number that satisfies the condition should be saved, right? So when I come to the for loop, I'm doing the same thing here anyway. So what I'm doing here is the same in the for loop, but the only difference was how I defined the argument in the for loop and how I'm defining it in the while loop. So the while loop always, when you consider the while, what you put here is like a stopping rule, so that if that condition holds, then it should stop. Okay, so here we are saying that first of all, it will start with when n is equal to 1, and it will ask, is 1 less or equal to 1,000? If it is true, then it will come to the condition and ask if the modulus of 1 divided by 8 is 0, or if 1 divided by 8 is 0, then it should save it as a multiple of 8. Okay, in the loop. Okay, so you should save it as a multiple of 8. And don't forget, I've actually considered saving the results as a list. I could have also saved it as a vector, but I told you can save it as a list, as a vector. If you are saving it as a vector, you have to create numeric or a number of zeros or a number of NAs or a number of fours or anything. You could even use your name and it will still work. But if you are creating it as a list, especially when you don't know the exact number of multiples of 9 of 8 from 1 to 1,000, you wouldn't want to create a vector first. You could either create a vector of NAs. When you are done, you can remove all the NAs and you still get the results, right? But I could just say a list, save it as a list, and when I'm done, I can do on list, or I can do omit. I told you that anytime I use list, then even if I don't on list, I don't have a problem, right? So if you remember now, if I should run this one, okay, you realize that I have, so the first condition didn't hold up to 7, and then the 8th hold, right? If I use on list around this one, it automatically removes all this now there. It removes it and gives me the exact number, okay? So keep that in mind. So that's why sometimes the list in bracket is sometimes useful. But if I had used now, see what happens. Then it will return n is if that condition is not holding. Then when it holds, then it gives the number, right? But if it happens that way, you can always write na dot omit in small letters, na dot omit around this, and then it will remove all the NAs for you. Okay, so don't forget that. All right. Okay, so now let's look at how the while loop, how it works. Okay, so first of all, here we are saying it's a stopping condition that if n is exceeding 1,000, it should stop literally. And now if it's considered when n is 1, then it asks whether that condition is satisfied. Then it comes to, so if indeed that 1 is less than 1,000, suppose if n is let's say 1,001, let's see what happens. nothing came, right? Because the first number I'm considering is not satisfying this condition, so it will not go to the if condition at all. It will only go to the if condition if whatever I am considering, I considered first actually satisfied. So I'm starting with 1, okay? And if that condition holds, it should test whether it's a multiple of 8. If so, it should save it in the as a list, okay? And don't forget to, this is what is now making the difference. So here, the first value of n will come here, and it will be, the first value was 1, so it will be 1 plus 1 is what? Is 2. Then the 2 will come automatically and start from here. Okay, so you start with something 1 outside the while loop, and it tests whether the condition holds. Once it comes in and the condition holds, now you don't need this anymore. Okay, so it means that with this function, it now asks when it initially it was 1. Okay, so 1, is it a factor? Is it a factor or a multiple of 8? If it's so, then it saves. If it saves, then it goes to the next so if n was 1, 1 plus 1 is 2. Then the 2 now starts and asks if 2 is indeed less. And if 2 is less, is it a multiple of 8? Okay, if it is so, then it satisfies the condition. If it is not so, it doesn't satisfy the condition, and it goes to what? 2 plus 1. That is when n is 3. So that is how the for loop actually works. Okay, so it's basically like that's how the while loop actually works. It's not very different from the for loop, but the only thing is that, as in the case of the for loop, you have to specify a sequence, the positions first, before you now what? You now consider each position and save. Okay, but with a while loop, you have to start with the first number in the sequence and put the last number in the sequence as a condition so that it won't exceed that, and before it now tests the condition. And if it tests the condition and it holds, then that number will increase by 1 and also start and does it iteratively as such. Okay, so that's basically, so at the moment, since I started with 1, if I run this, I get that. And since I'm not and don't forget, the n was because I used list. If I had used list in bracket, it will just give me this. If you use now, all you need to do is to bring na.omit. If I had used now, all I needed to do is to bring na.omit around this, okay, and it will just extract and remove the NAs. Okay, fine. So that is that for the loop. We will now see how we use the for loop to plot some graphs very soon. Now with our apply function, we wouldn't waste too much time here. So now here I'm creating a data. Okay, so here I'm creating an artificial data. So I'm calling the first column to be age. So the age I started with, and don't forget, I just brought a concatenate sign, and because I want to create a vector, okay? But the vector, since I'm not considering a sequence like 1 to 10, so I needed to, because I'm creating something like 5, 7, 8, 9, 10, 12, 14, 36, 50. So with that, I have to manually specify, and I will use the concatenate. And here I was creating a sequence from 1 to 30, and I want to return or extract only 10 what? Only 10 of numbers from 1 to 30. And don't forget that if you are creating a data frame, always the number of what? For each column, the number of how do you call it? The number of entries should be the same. So what I mean is that if this vector age I've created is having 10, the dimension is 10, or it has 10 elements, I cannot put, let's say, 9 here. If I put 9 here, I'm trying to say that it should return only 9 numbers from 1 to 30. If I run this, I'll get an error, okay? Because technically, the number of the entries or the dimension of each of the columns should be the same, okay? So I started with 10. All right, so with this, so here I've created a variable called age. It's just something I'm creating, and I'm creating something I name it size. And here I'm using the replicate function. Now, if you remember, I told you that if I write replicate, I put 2 here, okay? And I put 10 here. What this is doing is that I'm saying that it should repeat 2 10 times, okay? If I can put my name here. You remember, anytime I'm typing a name, we call it a string. If I don't bring the quotation sign, see what happens, you get an error, okay? So I'm bringing this. The only instance you not bring a quotation is when you think that that thing was was an object. If it's an object, you don't have to bring a quotation, okay? But this one is anything that I'm writing. So here I'm saying that it should repeat Clement 10 times. Now, if I put, let's say, 2, 5, and I put 10 here, what I'm saying is that it should repeat 2, 5. So it should repeat 2 and 5 10 times. So it meant is the first 2, 5 is the first one, the second, the third, and so on. So this repeat function is also very useful. And I even showed you that you can also use it in place of the numeric when you are saving your results of the for loop, right? So here I'm saying that it should repeat 2, 4, 5, 6, 7, which are 5 numbers twice. Twice means it's going to return 10 numbers. Do you get what I mean? Yeah. And then here too, I'm saying that it should repeat males and females. Okay. Don't forget males and females is considered here. It has been concatenated. And I'm saying that it should repeat this one 5 times. So repeating these two names 5 times is automatically going to be 10 in total, right? So for instance, if I should copy this and run that, so what I'm saying is that it should repeat male and female 5 times. So this is the first one, this is the second one, third one, fourth one, and so on. Okay. So with this, I've been able to create my own data in R. So this is how simple you can create. So just consider the first sequence, give any object name, the second sequence, any object name, then you just write data.frame. Then you put the first object, the second object, the third, the fourth. Once you do that, and then you save it into an object. Don't forget that if I don't save this one into an object, I cannot use it later. Okay, and that's why it's always good to save any of your codes in an object. So now I have a data frame with 10 rows and 4 columns. Now suppose I want to find the mean. You realize that you can only find the mean for the first 3 columns. I cannot find it for gender. And you also remember, now we learned how to do extraction. Suppose I want to extract the first column. We said that I could just put a square bracket here. Since it's a data, don't forget, if I bring comma, it means that variable is either a data or it's a matrix. If I don't bring a column and I put 2 here, it meant that variable was a vector. This object was a vector, and it's extracting the third position. Okay. Right now, if I run this, one, it's working, and the reason is because data frame is like a list. Each column is like a list. So for each column, I can either use comma 1 to extract the first. So if I use comma 1 means I'm extracting the first column, as you can see, the first column. If I use 2, the second column, okay? I can use 1 to 3, and that is extracting the first to the third column. This part is made empty because is the rows. If I'm interested in extracting the first 5 rows as well, I can put 1 to 5 and it works, isn't it? Fine. Now I want you to note that the data frame we're using is also a list. And to extract any entry of a list, you can use double square bracket. And if I put 2, it's also another way of extracting the first column. So it will do the same thing as if I had copied data and I had just used a single square bracket and put 1 in the column. Let's run this. You realize that it gives me the same result. So don't forget that you can also use a double square bracket and put any column you want. Suppose I want to extract the fourth column. I just have to put 4 here and it runs. Okay. If you put 5, since the number of columns were up to 5, if you run this, it tells you that the subscript is out of bounds, meaning that there is nothing like the 5th column. Okay, so don't forget that you can also extract each column of a data frame like a list. And I told you for a list we use the double square bracket to extract. But for some reason, it looks like of late the single square bracket is also working for list. At first, I didn't see that, but now if I just use a single square bracket, you realize that the single square bracket is extracting gender, it's extracting the first column, but it extracted it as a data frame. But if I use the double square bracket, it extracts it as a vector, like a single row vector. Okay, so keep that in mind. And so that's also one thing we've learned. Fine. Okay, so now suppose I want to find so we are considering the apply function. Previously, if I wanted to find the mean for, let me open this. If I wanted to find, let me open a cell. If I wanted to find the mean for the first column, I could have just written data underscore artificial and just use this to extract and just find, oh, I typed the wrong name. Let me paste this. Okay, so I could have just used the double square bracket to extract the first column as a vector. So don't forget that if I use a single square bracket and I put a value there, and it's a data frame, it extracts the column, but it doesn't convert it to what? To as a vector. So you saw that when I did this one with a single square bracket, it's also extracting the column, just as it would have done if I had used the artificial with this. Okay, so suppose if I should comment on this, if I run this, you realize that the first one is a square bracket without, sorry, let me put one here. So the first one is a square bracket, it's a square bracket without a comma. It still extract the first column. But when I use the comma, it extracts the first column, but makes it like a vector. You see, this one is making like a column, but it's a data frame. You've extracted the first column. Okay, but usually you want to work with vectors. When you extract anything, you want to extract it as a vector and make and because you can only multiply, you can do a lot of things with vectors. Okay, so and yeah, so don't forget that. And I told you can also use the double square bracket instead of the single square bracket if you want to also convert it as a vector. Okay, so you can also use this. So it meant the double square bracket and the square bracket with a comma. Okay, it's literally doing the same thing. Now, if you want to find the mean for the first column, so you can clearly just use this. But suppose I want to find the mean because don't forget the data. To find the mean, I could have just done for the three at the same time. I could have just find the mean for age, size, and height at the same time. And that is what this apply function is doing. So the very moment I write apply, okay, and I remove this, keep in mind you cannot put something like this saying that you want to extract the first three. It won't work. In that case, unless you use a square bracket, put a dollar sign here, a comma here, and extract the first three columns. Don't forget that. Okay, so don't forget that when you use the double square bracket, you can only put a single number there. Okay, fine. So here I'm extracting the numeric part, and the numeric part is the first three columns. And if I use apply of this, and I put 2 here, and I want to find the mean. What this is doing is that it's going to find the mean. The 2 here means that across columns. So, and don't forget it can be 1. So you see the difference when I make it when I make it 2 and when I make the same thing 1. Let's see the difference. So if I make this 1 and I make it 2, let's see what happens. So when I make it 2, what happened was it has computed the mean for each of the columns. So age, size, and height. Okay, so the 2 here, so 2 in the apply function represents find the mean of the first 3 columns. Okay, so don't forget that that's what the 2 does. And the 1 means that find the means of the rows. So the 1 finds the mean. So I've extracted this 3, all right? But the 1 is finding the means for each of the rows. So it's finding this plus 5 plus this plus 2 divided by 3, 7 plus this divided by 3. So there are instances where you have a data and then you've extracted just the numeric part, and you're interested in finding the mean, the median, the mode for the numeric parts at the same time. So this is what I meant by you could have also used the apply function in the summary statistics function we created previously in our first class. Because remember in the previous class, we created a summary statistics function that will ask if a variable is numeric, and if it's numeric, it computes some summary statistics and so on. And then if it's categorical, it computes percentages, and then it gives plots at the same time. You could have actually done the function such that it will extract all the numeric variables from the data, or the numeric variables from the data, and find the means, the medians, and everything at the same time, so that you don't have to just specify for the first column, then it does what you want. Okay, but suppose you want to be able to, for the function to pick up the whole data and find the means for all the numeric variables. If the numeric variables are 20, it should find all the means All you need to do is that if I specify all the numeric variables, the columns, and I just put means here and the mean here, and you put 2, it will find the mean of all those numeric ones, okay? And don't forget, I could just put sum. So suppose I want to sum each of the columns, column 1, column 2, I want to sum each of them. I can also just use sum and do that. If I want to find the mode, or if I want to find the median, I can just put median here and you run. And don't forget, you can create your own function and put it here, and it should do the same task for you, okay? So suppose you wanted to find the standard error. We know that the standard error, so suppose I want to find the standard error, and I created my own function, and I said function in bracket x, and I open this, and I say that, let's say error, okay, equals the standard deviation of s divided by, we know the standard error is the standard deviation divided by the length of the data, okay? And then I should not forget to return this, okay? So now I've created a function to compute standard error. I can put that function here, and it will find standard error for each of the columns. And that's what it has done. It finds a standard error, meaning that the standard deviation divided by square root of the data or the sample size. Okay, then don't forget that sample size was 10 in our case because it had 10 column 10 rows. Okay, so this is how useful the apply functions can be. So this is the apply. The first apply function is called apply. And then when you put 2 there, and you put 2 and you put any function here, it will do that function for each of the, or apply that function to each of the columns you specified. Okay. And then so suppose I had put 4 here, and I had put table. You realize that in this case the table doesn't work for the fourth case, because it's saying that the dimension of s has to be, yeah. So usually try and use that for only numeric variables, okay? So for numeric variables, you can do for, let's say, if it's just a single value you want to consider as the first column, when you use that, it doesn't work, because first of all, the very moment you put 2 here, you are telling it to do more than one column, okay? And that's why if I now consider this, then it will work, okay? Okay, this one I was extracting tables. Now I'm interested in, let's say, the sum. Then it will find the sum for column 1 and 2. So don't forget, the very moment you use the apply function, you should use more than one column, then it will work, okay? So if you want to challenge yourself, you can convert our summary statistics, the complicated function we've created. You can make it such that it should extract all the numeric variables, and then it should compute the means at once for all of them and return all of them as a data frame. It should compute the median at once for all the numerics. So instead of first of all asking whether it's a numeric or not, it should extract all the numeric ones, compute the means across all of them, and this can be used exactly for that, okay? And then I told you that if you put 1 here and I want to find the means across each rows, then you use 1 and it will do for each rows. And anytime you use the apply function, you have to specify more than 1 column. If you use only 1, you realize that I was getting errors, okay? Because it expects more, because the applied has been created in such a way that if you want to find the means of, let's say, three variables, you can use it. If it's just one variable you want to find, then you would want to do it separately by just typing mean around it. But if it is you want to do 3 at a time, you just specify all those columns, but don't forget that now if I put 1 here, I am doing it across what? Across each row. But if I put 2 here, I'm doing it across the columns, okay? So don't forget. So here I've said that the 2 is for the columns, okay? And then the one equals rows. The one in apply function is actually for rows, okay? So now if I put 1 here, it's for the rows. All right. And now there's another thing called T apply. So now we've learned apply, and we are now going to learn T apply. You know, technically, I could have just suppose now I want to find the mean. The first variable was age. The mean age for both males and females. If I want to find the mean age for both males and females, so I could have just used this and just bring a $sign, okay? and consider age. I told you can either use the dollar sign or the double square bracket, or a single square bracket, but with a comma, and you specify the column, right? So I can use this and put gender. Okay, so now what I'm doing is there are instances where you were just interested in finding the mean age. If we're just interested in finding a single mean age, don't complicate your life. Just write mean around this and run. You're okay. But suppose you want to find the mean age for both males and females. So the first here should be that numeric variable. Then here should be the categorical variable you want to find across. And you put the mean here. If I run this one, it gives me the mean age for both males and females. Okay, so with the t-apply function, you can actually use that to find. So if I wanted to find the sum, or I want to find the median, if a sum, I just put it here, it does what you want. So it was the mean age, it does what you want. Okay, you can change this variable, and then so mean that with this, you can actually use this to find the summary statistics of any numeric variable across any categorical variable. Okay, so you can use our first data set that we created in the previous 3 lessons, and try and use the t-apply functions to find, let's say, the mean of a certain numeric variable across some categorical variables. Okay, and it should work. Mode or anything you want to compute, and it should work. Okay, so that's for the t-apply. That's what we use. Now, what about the l-apply? So you realize that we use the normal apply function here. Okay, so if I should run this, okay, and I want to find the mean for each of these 3 columns, I have to, or these 3 variables, I have to put 2 here to indicate for columns, and then I put mean, and I run, and I get that age, the mean age is this, and so on and so forth. If I want to sum, I just have to put sum here. If I want to sum all their ages, their sizes, their height, I put sum, and I run, and I have this. But now you realize that I can also use l-apply instead of apply without the l. If I'm using the l-apply, I don't need to specify 1 or 2. We only specify 1 or 2 when I'm using apply. Okay, if I'm using l-apply, all I need to do is that put the column I'm interested in, the columns I'm interested in, and just tell me whether you want to find the sum, the mean, whatever you want to find. If it is median, just put median here. So you see, initially, if I wanted to find median, I'll type median around whatever I want to find its median. Now I can just find median with this, and it will do across all the 3 columns. So this is why I said that you can either use this l-apply function, the apply by specifying 2, okay, because don't forget the columns are always the variables. Okay, the columns are always the variables. It's not the rows. It's only when in a peculiar instance you're interested in the rows mean, the mean for the rows, that's fine. But if suppose the rows were across time, then maybe you want to find the means over time. That is fine. But if it's always the columns you're interested in, okay, so meaning that apply with the 2 is the same thing as l-apply without anything there. Everything is the same. The only difference is that there's nothing like 1 or 2, 1 for rows and 2 for columns for the apply. But for the l-apply, just have to specify the data and just put the function there. Now let's look at the difference between this and if I should change the l-apply to s-apply. Okay, if I change this l-apply and I change the L to S, see the difference. Let me run this. See the difference. So you realize that the s-apply converts the results as a vector. Always vectors are written horizontally, okay? But with the l-apply, you realize that it's printing out column-wise, okay? But with this, you can save it in an object. Suppose I put an object name called X, and I put S here and I run. It gave me the same thing. Now, suppose I'm interested in just the age. I can bring the dollar sign, okay, and then select the age, or I can use double square brackets and put 1 there because it was 3 columns and the first column was what, age, and put 1 there, and that will also select. So you can always use the dollar with a variable name or a double square bracket, and it should work. Let's see. If I use a single bracket, you saw what happens. If I use a double bracket, let me put a double bracket. If I put a double bracket, you also see the difference. So it meant the double bracket actually extracts the number in the first position. Here, if I put 1 here, it extracts the exact number in the first position. Or I can just bring the dollar and extract the name of the column I'm interested in. Okay. If I don't put anything there and I just print it out, I just have this. Okay. But usually you would want to save your results in what? An object if you want to use it later. Okay. And I said that the difference between the L apply and the S apply is that the L apply returns the results separately, but the S apply returns the results but converts them as a vector. So it will be on the same, like, so the same thing, there's no difference. The only difference is that once, and this S apply, suppose the L apply was going to return, let's say, three different, let's say, suppose it returns 2 columns. This one might convert it to a matrix. So always, this tries to simplify what this one has printed more. This one tries to simplify it in the simplest way. So that is that. So the S apply, the L apply, and the apply with the two can literally be used for the same thing. Okay, so don't forget that. So that's the importance of the apply function. And we said the T apply is when you want to find anything, the mean of anything, the median, the mode of anything of a numeric variable, but across some categorical variables. So you can use our old data that we created, okay, in class, and try and what? Try and then try and find the mean of the numeric ones and the sum, whatever, across the categorical. Okay. So that's basically that for that. So I wouldn't waste too much time. Now let's go straight into the simulation that I was talking about. And then keep in mind, is because I'll be giving an assignment next week, and the assignment will require you to have prior knowledge in most of the things you've done. Now here we'll see the advantages of for loop. Okay, so here I did a plot using for loop, so we'll come back to that. So now let's see something. So when we talk about simulation in statistics, we should understand that different disciplines have different definition for simulation. Okay, so when you go to when a computer scientist or when a computer scientist is talking about simulation, or someone who develops a game is talking about simulation, you see the games we play, the FIFA, those games we play, they are all simulations. So you see some cartoon, they are all simulation trying to mimic a reality, isn't it? So what simulation does is it tries to mimic a real phenomenon, right? So that is basically simulations, right? But in the context of mathematics, okay, we simulate random events or random phenomenon, okay? And then keep in mind there's something called probability distribution. I wouldn't want to explain much into that, but keep in mind that technically everything we do in this life follows a probability distribution. Now, if I want to record the number of road accidents that occurs, let's say, at a certain junction within a period of time, it follows the number of road accidents will follow a particular probability distribution called Poisson distribution. If you know that the average number of accidents that occurs in the junction is, let's say, 5, then we are saying that then the number of road accidents that occurs at that junction actually follows a Poisson distribution with mean 5. Okay, so since we know that the mean is 5, I can actually simulate the number of potential road accidents that can actually occur there. Okay, using something we call, like, for instance, R-Pois. So the R-Pois is simulating Poisson random numbers. I'll explain all these in details over time, but for now, we just have to keep in mind that, for instance, when you're writing an exams, okay, for each question, you can either fail or pass. Now, the chance or the number of the number of correct answers for, let's say, a single question, to get it wrong or right. Okay, if you get it right, you have one question correct, isn't it? So if it's just one particular question we're solving, the number of correct answer for that or failure for that follows something called Bernoulli. If you toss a coin, you can either get a head or a tail. Okay, the number of heads in that case for a single toss also follows a Bernoulli trial, okay, or a Bernoulli distribution. Now, if I'm considering 10 questions, and each question I can either get it wrong or what, or I can either pass or fail each question, then if I consider the number of correct answers I get, the total number of correct answers follows a distribution. And that distribution is called what? Binomial distribution, okay? And each distribution has some specific parameters, okay? So here, what I'm doing is that here we are not interested in knowing the distributions. All we are interested in knowing is how to simulate a certain distribution. So suppose I'm interested in simulating a binomial distribution, which I've explained that every real phenomenon As another example is if a mother is going to give birth or doing delivery, the mother can give birth to a male or female. Suppose we have 10 or 100 mothers who are giving birth and each can give birth to a male or a female, okay? If we are interested in the number of males, then it means that the event of males or the chance of getting a male is what we call success, okay? And then failure means in that case they were not interested in females, or you were not interested in females. You were interested in males. If we're interested in females, then what you're interested in is your success in terms of binomial experiment. Okay, fine. Now the number of women who give birth to the success or the number or the category of interest. So if I'm interested in out of 100 mothers, how many of them are going to give birth to a male or give birth to a female? That is a binomial experiment. Okay, it's a binomial experiment because for each mother, they have a mutually exclusive event or chance of giving birth to either a male or a female. And that is a Bernoulli trial. And if I consider more than one Bernoulli trial, we have what? A binomial trial or a binomial distribution. So I just want you to have a fair idea that everything in reality technically follows a probability distribution. So I wouldn't go much into the details, but just understand that everything we do. So for instance, it could be how much you spend, the money you spend every day. Technically, if we were to fit a distribution to it, it will follow a certain distribution, the amount of money we spend. Okay, so keep in mind that everything we do has a probability distribution, and then we can actually use simulation to actually mimic. So suppose I'm doing a study, and the study I'm interested in looking at factors that affect road accidents, let's say in Ghana, and I realized that they don't have any data on the number of road accidents in Ghana, but we have the average number of road accidents in Ghana. If I have the average number of road accidents in Ghana, and they said the average number of road accidents in Ghana is is 10 deaths per second or whatever, or per hour, I can actually use R plus because I know that the number of event that occurs within a small period of time or a period of time is actually a Poisson distribution. So if I want to simulate, let's say, 100 of such data points, once I know the mean, okay, once I know the mean to be 1, sorry, I said the mean to be, let's say, 10 deaths per that, I can just run this, and this one will give me that there was this. So this is a simulation. So this one, what it means is that it's assuming that there was 6 accidents in the first instance, there was 15 accidents at another time point, there was 10 accidents at another time point. So you can actually use this probability distribution to even simulate data that you cannot even obtain in reality, but you know that that data follows a certain distribution. Okay, so that's the rationale for this. And then later on next week, when you talk about central limit theorem, you would also embrace why I'm saying that. But I just want the take-home message here is that every phenomenon follows a probability distribution, and we use simulation to mimic a reality. And then, but in the context of statistics, simulating something like game, as we see people playing game, is different from the kind of simulation we do in statistics. So in statistics, suppose, for instance, in my PhD, I am trying to model the spread of parasites at some body locations of a fish, like as an objective. So in such a case, I can use simulation to actually do that, okay? And then when I'm doing that, I'll be making use of these random numbers and probability distributions as we've been seeing, okay? So keep in mind, these ones has an enormous significance to research at a certain level. But for now, we want to see how the histograms of this distribution. We want to see which of these distribution is skewed and so on. So now, suppose you don't know anything about the distribution, but you know how to simulate. So what we are doing is that we are simulating 1,000 samples from each of these probability distribution. We are simulating from binomial, Poisson, uniform, and uniform distribution is actually what we say in reality that if you want to do something where each observation has equal chance of being considered. So uniform distribution is actually what we use if we want to consider certain conditions, that if this condition holds, then something should happen when we are doing simulation. It's actually uniform distribution that we use. And we'll see that in the process of doing that Monte Carlo simulation, which I said we'll talk about shortly, is uniform distribution is going to play a very key role, okay? And if you've heard of stochastic processes, when you are simulating stochastic processes, we use uniform distribution to determine the type of event. Like my case, if I'm considering the spread of parasite on the body of a fish, and I'm interested in the parasite could give birth, okay, they could die, they could move, and then there could be immune response or whatever. The event for immune response to occur, I have to use a uniform distribution to determine the event, whether birth should occur, whether death should occur, and so on. So we'll see that in a Monte Carlo simulation. This exponential distribution too is very useful. I wouldn't go much into it, but the most important distribution you can ever or you should know is normal distribution. This normal distribution actually has given rise to when do we use a parametric model or non-parametric. So you find out that when we start the classical test hypothesis testing, we realize that there are instances when we want to use ANOVA, or we want to compare means across some groups, or we want to compare anything between groups. And when you are doing that hypothesis testing, you realize that the first thing we ask is, was the data we are using normally distributed? If it's not normally distributed, we'll be using something called non-parametric methods. And every parametric method has its non-parametric version. So for the normal distribution, just keep in mind, is one key term you'll be hearing throughout statistics. I mean, once you start even regression analysis, whatever we do, I mean, because if a data follows a normal distribution, it means that if you want to now do any inferential statistics, you can technically compare means, because we know that the mean is not affected by outliers. Sorry, the mean is affected by outliers. It's the median which is not affected by outliers. So if I'm using something like ANOVA to compare means across more than two groups, okay, whether there's significant difference in terms of the means of a certain variable across more than three groups, and the data is not normally distributed, it wouldn't make sense to compare the means, right? Because if it's normally distributed, it means that the means have been either inflated or or deflated, okay? Or the mean had been very high or low due to outliers. So in that case, you might want to test medians, and you know the median is just the middle number. So if the extreme is super large, we don't care. But if the extreme, suppose the maximum data, the maximum value of a data is, let's say, 10, and I increase the maximum to, let's say, 20, when you find a mean, clearly you can see that it will change. If I increase the maximum, the mean will increase. If I decrease the maximum, the mean will decrease. But you realize that the median, which is the middle, would never change, even if I decrease the least value or I increase the maximum value. So that's why the mean is always useful, especially for non-parametric tests. So non-parametric tests usually try to test the medians when the parametric tests are actually doing more of the mean, okay? And even with regression, we are fitting the mean distribution. So keep in mind that if data are normally distributed, it actually motivates the choice of or the type of model we use. Lognormal is like a form of logarithmic transform of normal distribution, so it's nothing strange. All right, so here we are trying to simulate from this distribution. So here, keep in mind that every distribution too can be characterized completely by its parameters. So for now, you're not supposed to know what the parameters are, but just keep in mind that for binomial distribution, it has two parameters, which is the size and the probability of success. So here I'm saying that the size is 10, and then the probability of success is what? The probability of success is, let's say, 0.5. Okay, so what I mean by the size is 10 could be, so suppose, let's say, you are doing 10 questions, okay? If you are doing 10 questions, right, it means that the total number of questions is 10. And if suppose you have a chance of 5% of answering a particular question correct, okay? So technically, if it's an objective question and there are 4 possible answers, you have a chance of 1/4 of getting it correct, isn't it? So in that case, 1/4 would have been my success here. But here, we don't want to attach any phenomenon to this binomial distribution. Let's assume we are just simulating 1,000 binomial samples with n, the size being 10 and the probability of success being 0.5. And for the Poisson distribution too, the mean is characterized by S lambda. Okay, here I'm just simulating a Poisson distribution with mean 1, and uniform 2 is bounded by the minimum and maximum. So here I'm also simulating 1,000 what? So if you use R unif, if you use the R here means random. Okay, so the R here means I'm simulating a random sample from binomial. Okay, so you will see something like R binom, R poise, R unif. So meaning that simulating from uniform, if it's simulating from exponential, I'll use RESP. If it is normal distribution, I'll use R norm. If it is log normal, I'll use RL norm. Okay, so keep in mind that that is it. So now see how I was, because I want to plot the mean, I want to plot the histogram. I could have just plot histogram for the first one. Okay, so I could have just used, let's say, x equals, and then I copied this one, let's say binomial. Okay, so now I've simulated 1,000 samples from binomial with these specific parameter values. Okay, I could have just used histogram around this, and then it will give me the histogram. Okay, I told you usually for what do you call it, to increase my plot size, I use something to increase the size. Let me just, excuse me a little bit, let me just get that second I script, second. Okay, yeah, so I'm just copying a code here just to increase the plot size in Jupyter Notebook. And then keep in mind, next 2 weeks we will have a specific class on how to use Jupyter Notebook, so how to download. So that class, so in next 2 weeks we won't actually do actual learning in terms of statistics. We would actually learn how to use Jupyter Notebook, because it appears, you can clearly see that it's more useful than the R Studio. Okay, so don't forget that we'll be using that shortly. Okay, so this is what I wanted to copy. Okay, so if you already have code to something, a previous thing you were doing, you can just go and copy, and then yeah. Okay, all right, so now let's come back to what I was doing. All right, so here I want to increase the plot size. Insert above. Okay, but there's one thing I want you to note. Now, if let's say with a binomial distribution, suppose I'm just simulating 10 samples. See something. If I run this, I've simulated 10 data or samples from binomial. Okay. Now, if I run again, let me come down. I'm running the same thing again. See what happens. I'm getting different values. So that's what we mean by a random variable. Okay. So meaning that this one is simulating numbers randomly. Okay. So because in reality, data is never static. There's a lot of randomness in data set. So when we are simulating, we get a lot of randomness. If suppose you run this code right now on your laptop or in R, when you run, you get different. So you see, anytime I run, I get different outcome. Anytime I run, I get different outcome. If we want to get the same outcome, I just have to set something called a seed. So I can use set.seed. I can put any number here. Okay. So now if I run this and then I also run it down here, you realize that the answers are the same. Meaning that if you now also run this function and set the seed to be 1, you get the same answer as what I did. Okay, so so people, when they are doing your publication, you realize that there's a problem called reproducibility. So you cannot reproduce some people's work, especially when they were doing some studies which had a lot of randomness, or maybe they were doing a lot of simulation, and then they could have set a seed such that if I also want to confirm all their findings, I can also use their seed number and it should give me the same results. But the very moment you fail to set a seed and then you are doing this simulation, it meant you yourself will never be able to get back what you already had, let alone other people trying to get your results. Okay, so keep in mind when you are doing probability distribution, in terms of when you are simulating, you always have to set a seed. The seed, you can put any number, it can be anything. Okay, so it means if you don't specify that seed number and I run this, I'm getting a different result from this. But the very moment I set the same seed number, I get the same results. Are we okay? Okay, so keep that in mind. So now, so if I wanted to do the histogram plot, if I had now I've simulated 1,000 samples from binomial, and I can just type histogram around X, and then it will give me, did I run? Okay, let me run this, and then if I should run this, yeah. So it gives me the histogram plot. Okay. Now keep in mind that with this histogram plot, if I run again, I'll get a different behavior because I've not set a seed. So it's always advisable to set a seed, especially if I want you all to get the same output as I had. So that's why here I've set a certain seed and saying 1, 2, 3. So when you are running and you forget to what, or you forget to what, specify this seed, okay, or you change the seed number, your output will be different from mine. But if you specify the same seed number, no matter the computer you use, you are supposed to get the same results as mine. Okay, fine. But instead of trying to do the histogram for each of them separately, okay, you know, this one I could have also considered y equals then Poisson. Then I also copied this Poisson data and then I paste, and then I now have to also use histogram and probably histogram of y, and then I probably would use, let's say, PMF row equals, let's say, 2 by 1. I told you you can use this one to combine multiple plots. So I could have done this, and then I have histogram of the 2, right? But imagine I have to do the same for all the 6. Meanwhile, I could do just a single line of code. I could do that with a for loop. Now see, with the for loop, this is what I'm doing. So now, that's why I saved each of the objects with a list. So you see, I could just write now. I could just write now. I could have just written list with this, or I could have just written the concatenate sign empty, right? And then when you do that, then you put, so here, so at the moment when you specify this and you try to run what you said is now, this is what happens. So if I run this one, you realize that it tells me it's just now. Okay, if I should change it to the list, okay, yeah, I mean, this is what happened. It's something empty. Okay, fine. So the very moment I stick to the now, I can now consider, let's say, something and give a different, and I can put one here and write any code and use this as an object. So that is basically what I did with this one. So now the binomials samples, I'm saying that it should be saved in the first list. The Poisson should be saved in the second list, because if I save them in a list, I can now write a for loop, okay, without necessarily having to do the histogram separately for each. So see what I've done. So now I'm saying that for I, and you realize I'm using sequence along the names. So here I just wrote the names here because on top of each of the histogram, I want to put the actual name of the distribution, okay? So I just wrote the names in the order of how I save the list. So the first one is the first here, which is binomial. The next one is Poisson, uniform, and so on. So here I told you that I could have, in the for loop, I could have just written, inside the for loop, I could have just written I in 1 to length, the length of this, okay? So if I type the length of the names, I'll still get, because the length of I'm considering 6 different distributions. So if I put length of the names, it will tell me that that object, okay, or that particular vector had 6 entries, okay? And then 1 to that means it should simulate a point or a vector from 1 to 6, okay? Fine. Now I could have just used sequence along without having to specify 1, then 1 to the length. I could have just used sequence along, because I told you if you use sequence along, it actually gives the position. So here it tells me that we have 6 positions in the object called names. So the names have entries 1, 2, 3, 4, 5, 6. Okay, so that's basically what the sequence along does. So I always prefer the sequence along to using the one with the column and then the length of. They will do the same thing anyway, but I mean the sequence along is the best. So with the for loop, it will first of all consider the first position, and here you realize that I want to choose different colors. I could have just specified blue. I could have just specified blue here, okay? But if I use blue like this, I didn't run this first. Okay, so if I specify blue, all the colors will be, everything will be printed in blue. That's not what I'm looking for, okay? I want to choose different colors. And you know, in R, if you don't even specify the name of the color and you put a number, do you know it also gives a color? Every color has a number, and black is 1. And then if I put 10, suppose I don't know what color is at 10. If I put 10, it tells me that 10 is red. So that's why, since you don't know the numbers, you could literally just bring a quotation and just put red, and you also get it, right? But I want to choose different colors. So since here we have 6 different positions, if I put I here, it means that when I is 1, it will choose the first color. When I put I to the 1 here, it's going to extract the first probability distribution, which was what? The binomial, okay? So here, it will first of all consider when I is 1, and then it will choose the first probability distribution, choose the first color, and here I'm using something called paste. I told you, you can use the paste to paste anything, right? And if I use paste, you can even separate paste with commas. If you remember here, I could have just written paste. I could have just written paste, paste, and then I can bring maybe positions, okay, and then positions, and then I can just run this. So I told you that for the paste, we can use paste. So here it has considered position 1, position 2, position 3 by just bringing here. So paste, with the paste helps us to what? Add extra text to what we want to what? Return. So here I just want it to paste the names, but the names I'm extracting. So here I brought, because the names was saved as a vector, I brought a single square bracket so that it will extract. If I'm doing for the binomial, it should extract the first name and paste it here. If I is 2, the 2 will be here, so it will extract the second sample, and then it will choose the second color, and then here it will choose the second name, okay? But the x-axis I want to what? Have the same x-axis. Suppose I wanted to vary the x-axis, I could have also used the paste and then put something that to make it vary, okay? So now if I run this one, it meant that I've been able to what? I've been able to get my histogram plot, and it has chosen different colors. And don't forget, I use a single, just look, I just use a single line here to do everything at the same time, as opposed to trying to do histogram separately for the first one, histogram separately for the second one, and so on and so forth, okay? So that's the one of the beauty about the for loop. So the for loop is not just extracting sequence of numbers as we're doing. You can actually use the same for loop, especially if you've saved some object as a list. You can put the for loop around it, and it will extract, it will do everything for you, okay? And don't forget, the for loop works in this way, where it will do for the first position, okay? And after the first position, it will go to the second position, it does the plot, then it goes to the third position, and it does it, okay? Fine. And then if you've done statistics a little bit at the highest level, you realize that there's something you call bivariate normality. If you plot two normal distributions together, it forms a certain shape, and the shape is an ellipse. Now, suppose I have considered 10,000 data sets from a normal distribution with mean being 2 and standard deviation being 1. I told you that every probability distribution has some specific parameter. For normal distribution, all you need to know is the mean and its standard deviation, or the mean and its variance. Once you know the mean and its variance, you can specify how many samples you want to get, and you get it, okay? And here I'm considering the mean to be 2, but the second one I'm considering the mean to be 3. I have set a seed so that you can reproduce my results, okay? And here I am plotting, it's more like I'm doing a scatter plot. So I'm plotting the first sample against the second sample. So if we're in a statistics class, we said that if you plot two normal distributions, you should get something that is bivariate normal, and that looks like, in terms of in terms of a two-dimensional plane, it should look like an ellipse. But now see something. So I'm running for 10,000 samples. So you see, we are having something which is behaving like a shape, and this shape is like the shape of an egg. But will you believe that if you are to increase the size, the shape will be more prominent? You see the shape better, meaning that as you increase sample sizes, okay, the degree of normality also kind of increase. Now see, before increasing the sample, this is what we have. Initially, it was 10,000 samples I plotted against each other. Now I've made it 1 million. Now with the 1 million, see what happens. So it's taking a little bit time, but it will come very soon. So the more you increase, so this one I'm just trying to prove a theorem. So you realize that this is not behaving like a sun, okay? And this is technically an ellipse. And keep in mind, if you plot two large normal samples, you would always get something elliptical, okay? So keep that in mind. And here I chose blue color. You can choose any color. So this is just to prove a theorem. And then, so meaning that you were learning your statistics at that point. We said if we are to plot two normal distributions, you get something that looks like an ellipse, and you don't know, okay? Or even if you are testing whether two variables are bivariate normal in terms of normal distribution, which I don't want you to understand for now, you realize that you have to check whether we use some test, and the test will check whether something falls in a ball. or something falls in an ellipse. And this is actually what they were trying to mimic. Okay, and I just use simulation to explain here. Now with the Monte Carlo simulation, because our time is a little, because we didn't start too early. Okay, so this is the last thing we are doing and we are ending. So here with the Monte Carlo simulation, I told you that what I just did, you see, all the things we're doing, the probability distribution, the simulations we're doing, they were all types of Monte Carlo simulations. Okay, so Monte Carlo simulation is just, and the Monte Carlo simulation is all about trying to make use of these random numbers, okay? Decide when an event should occur, and if it occurs, it should do something. That is basically what the Monte Carlo does. So if I'm simulating a stochastic process, it means for stochastic processes, it is always, and you know, every event is stochastic. In reality, if you're going to give birth to someone, the person could be a boy or a girl. It's a stochastic process. Stochastic means that it's something that is not deterministic, or it's something that you don't have a specific degree of certainty. It can change, okay? So suppose you are tossing a die. When you toss a die, you can either get a 1, a 2, a 3, or any phase. So that alone is stochastic, all right? So now with the Monte Carlo simulation, what it's doing is I'm making use of the same for loops. The for loops we're creating, we are using that and we are considering a condition. Now, what I'm considering now, if I should run this code, okay, I'll explain what the code is doing. If I should run, this is doing like a toss of a die. If I run this one, you see, it said after tossing this die, phase 3 occurred. If I toss again, phase 2 occurred. Okay. So what are we doing technically? So here we generated something called a number. So here I'm considering n to be equal to 1. If I consider n to be equal to 10, I'm producing 10 samples from a uniform. Now I'm just interested in one sample, but I'm saying that it should be between 0 and 1. Okay. So keep in mind, for instance, if I should open a cell here, so this is the last thing, so we'll finish very soon. So if I'm opening a cell here and I run uniform, so here I'm just simulating one single number, but it should be between. So you realize that every number I produce will be something between 0 and 1. It can never be below 0 or above 1. So see, and anytime I run, I get different outcomes. Can you see now? This one is 0.8. So here what we are doing is that if I run, let's say this, okay, and don't forget, we are simulating using the Monte Carlo simulation. I told the Monte Carlo simulation is nothing but trying to use some random variable like a uniform, for instance, to determine when something can occur. And if it occurs, it should do something. That is all. Okay. And we are just using the uniform the distributions that we try to plot here already. So we are just using a uniform, because I told you that the uniform technically is what represents what we usually say if all things being equal, okay? Because here with the uniform, any number that I get from here has an equal chance of being selected, as opposed to if I use, so keep in mind, so with the probability distribution, what does it tell us? Look at the normal distribution, okay? Normal distribution here, you realize that it tells us that the most probable numbers or samples occurs at the middle. So you can see that numbers around 0 has the highest what? The highest mode. Or did I say the highest mode? Is the mode, or has the highest frequency, okay? For uniform distribution, for exponential, it tells us that numbers that are very small has a higher chance of occurring. That's why numbers that were very small towards 0 had the highest frequency. Okay, so it means that different distributions can tell you some degree of skewness. Okay, and some distributions are skewed to the left, some to the right, and so on. And for normal distribution, you realize that the degree of skewness to the left and right is literally the same. It doesn't stretch, the rate at which it stretches more to the left is the same as the rate at which it stretches more to the right. But for the for the exponential, I realize that it is very probable, or the frequency is very high for small numbers, and then as the samples increases, then we have the frequency also decreases. Okay, so this tells us that if I want to do the Monte Carlo simulation and I want to consider fairness, I wouldn't simulate from exponential, because for exponential, if I should simulate from exponential, numbers that are what? Numbers that are very small has more chance of being selected. So it means that if I wanted to say if something holds, that is if something is greater than 6, okay, then something should happen. That thing has a probability, it has a small probability of occurring, because if I use exponential, 6, just look, 6, the frequency for 6 is very low. But if I use something zero, did I say something between zero, I mean close to zero, like one, then one will have a more chance of being selected if I'm dealing with exponential distribution, okay? But if I'm using uniform, look at the uniform. For the uniform, you realize that I've simulated different samples, okay? But for the uniform, you realize that the rate, because this one I considered one instance, you realize that other, like for instance, this particular value is even though it's bigger than this, but it's not very big, okay? And if I had increased the sample size, everything would be the same. Instead of just seeing a single, everything would have been the same. So suppose the uniform here, if I should increase this uniform to, let's say, from 1,000 to what? From 1,000 to 10,000, and I run this. Let me now run this plot and see the uniform plot. So you realize that the more I increase, the frequency for each of the observation becomes almost the same. If I increase it again for the uniform, okay? If I increase it again for the uniform, see what happens. Then everything is almost the same. Yeah, so I want you to keep in mind that for uniform distribution, if we are to increase the number of times you are sampling from it, you are going to get a very fair sampling, or a very fair samples, or the samples you get will not be biased. Okay, so keep that in mind. So now let me just reduce to the 1,000, and then go on to the last. So, and go on to the experiment we're doing. So fine. So here, this random number I've used here, which is a uniform distribution. So I want to now, as I said here, if I run this one, I get some specific values. Okay. So here, what I'm saying is that if the number is, because a die has 6 faces, I'm saying that if the outcome from here, okay, if it is less than 1/6, then it should what? Print out phase 1. Printing out phase 1 meant it's more like you toss the die and you've gotten 1. But if it is something less than 2/6, don't forget, if I say 1/6 for the first case, and I said if it is less than 2/6, is the same thing as saying, it is the same thing as saying that if I is actually between 1/6, okay, and then between 2/6, okay. But since I've already said if it is less than 1/6, it should print the first phase, or phase 1, meaning that you've gotten the first phase. Then if it is less than 2/6, is the same thing as saying if it is between 1/6 to 2/6, then it should be, say, phase 2. Okay, so now it means the very moment if I run this and I had phase 6, it meant the random number I generated, okay, was something that was above 5/6. Okay, so keep in mind here, I could have just said else if let's say the I is greater than 5/6, okay, and then it will still work for me. But the very moment you forget to bring anything like if else, and you just say else, what it does is that if this condition holds, then it will print phase 1. If I is less than 2/6, it should print phase 2. If I is less than 3/6, it should print phase 3. Don't forget, if I say less than 3/6 in this case, it meant if it is between 2/6 and 3/6. Okay, don't forget that. And then when I get here, and the last but when I say if it is less than, if I is less than 5, so this I is if what I got from the uniform sample, okay, if it is that value, that proportion, if it is less than 5/6, then it meant I've gotten a phase 5. Else means that if it is anything that is outside all the conditions are specified before, then it should print phase 6. Okay, so basically that is what this is doing. So this one is just like you would have tossed a die. Okay, so if I run again, I get something. If I run again, I get different phase. So suppose you are doing like academicians have met, and maybe you want to do ballots. You can actually use this one for games. Those who would have used a die to play, okay, we want to see who gets the best phase or something. You could actually use this one for your games, okay, because it's behaving like you were tossing a die. Now, suppose I want to know how many phase 1s occurred, how many phase 2 occurred, and so on. Don't forget now, I use something called count, and I use replicate. Don't forget the replicating 0 6 times is the same thing as saying numeric, and I put 6. Okay, so if I consider let me open, so we are done. This is just the last thing. So if I run this one, it's actually similar. It's actually producing 6 zeros. Okay, a vector of 6 zeros. And if I use replicate 0 6 times, if you've already watched previous what I was talking about, this also does the same thing. Okay, so I can either use numeric or whatever. So here, what I'm trying to do is that if this condition holds whilst it is printing out phase one, it should also be counting how many times, okay, that I get what it should count how many times that I get one. So that is what I'm using the count here. So don't forget that here extracting the first one means that this count is like a vector. I told you, if you want to save anything in a for loop, you have to create a vector or a list or something to save it. Okay, so here I'm saying that for the first one, this first one, okay, once the condition holds, once whatever I got from the uniform actually satisfy this condition, it should increase the count by 1. If it satisfies again, it increases to 2. If it satisfies again, it increases to 3. Okay, so that's basically what I was doing here. But because here I was considering n to be 1 meant that I'm tossing the die only once. If I consider n to be 2, okay, see what happens. If I consider n to be 2, it meant I'm tossing the die 2 times. So it means that if I run this one, the first time I ran, the first one was 1 and the second was 5. Okay, when I run again, it meant I had 1 in the first toss, I had 1 in the second toss. If I run again, it was the same thing. If I run again, this is what I have. Okay, so don't forget that the number of times you choose the sample from the uniform tells the number of tosses you are actually, or the number of times you are tossing. So now it's just 1. Okay, so now I'm going to increase it to 100 tosses. But the focus of the 100 tosses is that I want to still keep track of how many times 1 occurred, how many times phase 2 occurred, and so on. That is exactly what I was doing here. Or what I've done is that I'm increasing n here now to what? 200. Okay, fine. So here I'm saying that the tosses is what? 100. And then so n is equal to the number of tosses. Okay, so now see what happens. So if I run this, nothing popped up because here what prints is due to the fact that I use a print function. So here I use something that if this condition holds, if the random number is less than 1/6, and then it increases the count by 1, it should print out phase 1. Okay. Now if I bullet, or if I comment or I push hashtag before them, you know that it now becomes like a comment. So anything you print will not actually come out, right? So because at the moment I'm not interested in the printing, I'm not interested in the phase, I'm interested in how many times 1 occurred. So now if I now type count, okay, see what happens. So this one tells me that when I run 10 tosses, 100 tosses, 1 occurred 15 times, 2 occurred 18 times, 3 occurred 14 times, and so on. And then we said that a die is supposed to be a fair die. Didn't we say that usually our die is supposed to be a fair die? A fair die means that the chance of the chance of getting 1 should be equal to the chance of getting 2, and so on. But keep in mind that the fairness only comes in play once you do the number of tosses a large number of times. So at the moment you realize that there's nothing fair in this case, because 5 is occurring more than the others. In this case, if I should run again at another instant, 1 is occurring more than the others. Okay, and I can use a for loop and sequence around the counts and then print each of the counts. So what I just did, I can just use this and I just put die number I, then so the I will print the first position. So die number 1 appears. So it's just this one. I'm just trying to use a for loop and attach some text to it, and then you can practice with that. Okay, fine. And here you can even plot a bar plot, okay, just to see how many times. So here tells me that phase 1 appeared more than the others. Okay, but suppose I want to get a fairness, I have to increase the sample size. So now at the moment you can see there's no fairness here. If, like, let me increase the number of tosses to 10,000. If I increase the number of tosses to 10,000, let me see the number of times each occurs. So you realize that when I increase to 10,000, now we are getting all of them occurring about a couple of thousand times. Now, if I should plot this this bar plot, now you realize that the bar plot is not, it's still, you can still see a little bit of biasness because some phases still appear slightly above. But the very moment I increase the sample size further, So this is when we say Monte Carlo simulation actually performs better when you increase the sample size, because I wanted to produce a fair die. So now I've increased it to over 10 million. Okay, so if I run this one, it tells me the number of times, and you can see when I increase it to over 10 million, now each of them is occurring about a couple of 160 something, 160 something. So for this, if I should run this one, you can clearly see that we have the bars are literally the same, and this supports the assertion that when you use Monte Carlo simulations, okay, so the Monte Carlo simulation is trying to say if we use a probability distribution to determine when an event or something should occur, okay, and then you want to, for instance, if it's a toss of a die, and you want to get and you make it a very fair, okay, the more you increase the sample size, the more you get fairness. So at this stage, you can clearly see that if I toss it a large number of times, then the chance of each of them occurring is the same. Okay, now suppose I wanted to make this die a biased die. You realize that here I said if it is less than 1/6, then it should print phase 1. I could have said if it is less than 2/6. It means that the more I increase this condition to, let's say, 2/6, and I make the rest to be very small, then one will occur more times than the others. So it means that in order to make your die biased, so if I want 4 to occur more, I just have to make sure I increase the interval, or the interval for which 4 will be printed. Okay, so that is how you make the die bias. Okay, so to make it bias, you just, so for instance, if I want to see more phase 1, I would rather, instead of 1/6, I would just say if it is less than, let's say, 3/6. So for instance, if I do this, now I'm going to be printing. Now let me say I've used 5/6. You realize that most of the time one will occur, because I'm now making it biased for it to choose one more. Now let's see what happens. So anytime I run, I'm now getting 1. At a point it could change, but the chance of it changing is very small, because I've made it such that the probability that 1 should occur should be something very close to 1, 5/6. Okay, so technically, if I want to make it fair, then it should have a chance of 1/6 of occurring. So I start with 1/6. The other one would also be, so 1/6 here means that from 0 to 1/6. Then the other one will be from 1/6 to 2/6. Then the other one will be from 2/6 to 3/6. So you realize that they will have equal chance of one being selected if I should increase the number of simulations. Okay, so basically this is all for the Monte Carlo simulation. And so let me just wrap up what we've studied. So basically, next week we are going to start with the central limit theorem, and then we'll talk about what the central limit theorem is doing. And then don't forget, we'll be making use of the probability distribution that we did. And then we'll introduce something we call two important methods of estimation. One called bootstrapping, and the other called jackknife estimation. It's very important, and we just want to learn that. And then as we are learning, we are making use of the same things we are using. The for loops, we'll be making use of them. And that's why I actually introduced it for the class. So, so at the end of this class, all what we did, or all what we learned for today, was to introduce a very important concept called for loops. And we said that called loops. And we said that for loops, we have we have for loops and we have while loops. And we said for loops, always you have to write for, then you specify whether I or K or anything in a certain sequence. The sequence is always the positions, okay? So the sequence is always the position. And I said you can either use 1 to, you cannot start from 0 to, keep that in mind. You cannot start from 0 to something in the sequence. You get an error, okay? Don't forget, in Python, always the first number or the first position is 0. But in R, the first position is always what? Is always 1. And don't forget, in the for loop, if I say K in something, that thing is only considering what? The first position, and then it goes to the next position and so on, okay? So we said for the for loop, we just specify the for loop, and then if there are any condition, we could have actually used a for loop without adding a condition, right? We only add condition when it's necessary, depending on what you want to do. I could have just created a for loop to print out, let's say, I could have just, let's say I'm printing out the square of numbers from 1 to 10, okay? So I could have just used a for loop and just put print, and I just say K square. So K square means that it will, first of all, so here, don't forget I said K in this, it should print the K, the actual K. So it is considered the first value of K. if this k, if it was a rather a vector, I would have rather put the vector name and bring a square bracket around the k, and that would have like right. I would have written that vector name will be here, and I'll bring a square bracket to extract the positions. Okay, but now I'm actually not interested in the position. I'm interested in the 1 to 10 itself. So that's why I'm using the k directly. I'm not extracting anything. I'm using the k directly. So this one is printing out the square. So if I run 1 to 10, if I should run 1 to 10 here, okay, now what I've done is printing out the squares of each. Okay, so here is printing out the square. If I want to print the cube of each, or the cube, I just put this, it's also print out the cube, okay, for each number. So the first number, it cubes it, then it goes to the next one, then it cubes it, and so on. So for loops and while loops are used for doing certain things sequentially, but doing it across the entire space you are interested in. Okay, so that was the essence for the for loop, and we said that we can even use the for loop in the process of plotting several graphs at the same time. All I need to do is that, suppose I have 5 or 6 different things I want to plot, I can create a list and then store each one, the first one in the first list, the second one in the second list, and just use, if I'm plotting histogram for all of them, I can just use a single line of code. If I come down, I can just use a single line of code with the same histogram, and then just consider a for loop. It will do for the first one, then after that it goes to the second one, and so on. And we've learned that for the color choice, if you even put I to be 1, it will choose black. Suppose you don't know each color in R and the position, just type the name of the color by bringing a column and the actual color name. Fine. So we learned that. So now we've introduced looping, and we said with the looping, you can use it to generate any sequence of numbers. You can actually use it to generate sequence of multiples of a number, let's say multiples of 10 from. So I think I gave a task here, because this will be uploaded in Piazza, and you can also download it. And don't forget, I would always prefer you downloading the HTML file over the R script. The reason is because you see this one, you will see the codes, and the output will just be below it, so that if you run your results, you are expecting to see the same thing, right? But for the R script, it will just be the script you are running. But for the HTML file, if you download the HTML file, you can easily copy and paste the codes. Also paste it, create a new R script and paste it and run. And so you can check the kind of output you are expected to see. Okay, so it's very useful if you download the HTML file, but the R script will also be uploaded anyway. But what I'm trying to imply is that with the HTML file, you can also equally copy and paste the codes into a new R session and still see the kind of output you're supposed to see. So don't forget that. Okay, so that's just something I wanted to tell you. And we introduced some form of simulation, and we said that simulations are very useful. For instance, now I was just considering tossing a die, and we've been able to create our own experiment that can toss a die, and it has attached some degree of randomness, that anytime you toss it, I mean, it could be 1, it could be something, and whatever. And we learned that for Monte Carlo simulation, it's just nothing strange, but it's like trying to simulate a random phenomenon where you use some probability distribution, specifically a uniform in most cases, to determine which event should occur. And if the event occurs, I mean, if the condition occurs, that event occurs, and then so the condition, so there's always a condition that it may be, if something is less than a certain threshold, then this event should occur, 1 should occur. If it is less than, if it is between this and this, then maybe 2 should occur. So it means that is actually the context of what? The context of Monte Carlo simulations. And Monte Carlo simulations are very effective if you increase the sample sizes, okay? So, or you increase the number of times you are doing the experiment. So yeah, so this is just, so this is the end of our class. And then see you next week. And don't forget, it will be uploaded on YouTube. And don't forget to also subscribe. And thank you very much. And more grace and more grace to, whilst you are learning, try and always develop this attitude that programming requires some sense of what? Sacrifice. If you don't invest time, you will never be strong. And all these things we are doing, once you start learning the course and then you start practicing, everything will just pop up. You understand what is really happening. You just have to sit down, watch the video once again, and everything will be fine. Okay, so don't feel intimidated if you didn't understand anything. All right, so see you next week. And if you have any question, you can actually ask me at the end of the class. Bye.